So good evening all of you. We will start with the just a high level overview of what we want to do. So let us first see what is the important thing in this code which you should understand is this portion of it. Okay, this is the brain of this whole algorithm. If I want to call, why do we use TensorFlow at all? Why can't we do everything ourselves? In fact, we are doing everything. We most of the time we do a setting up of things for the input data. We write the equation and then we write the output graph, we plot. Mostly this actually takes, in this code actually this takes almost 70% of the code, and the meat of the whole thing is finding the gradient and then updating the weights. That's only is the brain of this whole algorithm. Okay, so it's a very simple one, just to understand how TensorFlow works, so that you can build on top of it. Okay, that's the intent. Otherwise this is a very small code. Okay, so what we want to do, given an equation, this is the equation we would like to implement. When I say implement means I have a set of points which are distributed around this line. Okay, set of points which are given around this point. Now if I have to give something around this point, I have to add a noise, Gaussian noise or normal distribution. Now should I add the noise to X or to Y? Okay, should I now add it to X or Y? This is very subtle point which you might have realized it. If I add the noise to X, that's an input. Okay, instead of, maybe if I want a point at 1, what is the value of Y at point 1? No, X is 1, what is the value of Y? When X is 2, what is the value of Y? Is what is that we are giving. Okay, we are giving some sample points which is 120 in our case. But if I add a noise to this, actually in fact what I will do, instead of 1, maybe I will get at 1.1 and 2.3 maybe, or 4.6 or maybe 3.9. So I will be getting, instead of these exactly EQ spaced samples, I would be taking a sample which is around that point, and then I will get the exact value of Y, mapping it to this particular equation. So if I add X, if I add a noise to the value of X and then get a Y out of it, I will still get a straight line, because I'm sampling maybe at a different points. I'm not getting any a noise added to the value of Y, which is what we need. So what we need to do is, Y equation is given, maybe some X value we have chosen, EQ spaced values from 3 to 6 or whatever, and then we add a noise so that we, though this line exactly predicts the output, we are displacing it with some noise. So you will get all the points around this line, not exactly on the line. So that is a subtle point you should understand. If you have seen the code, you can modify that noise, adding the noise. Right now I think what I shared with you is here only, plus noise. What if I do X plus equal to noise, okay, and then I do X of this, Y of equal to this value, then you will not get any deviations in the points. Okay, that is one important thing which you might have noticed it. I am just getting it from 3 to 0, 0 to 3, and then I explained about this line rate. Okay, this is very important point to remember, especially for the exercise which you will be working on. You should understand the implication of this very clearly. So our gradient algorithm gives you some error, okay, or a loss. Now how much of it you want actually take, a sample of this you want to take, and then update the weight and noise, weight and bias. So how much of this you want to apply now, whether you want to take it fully or you want to take a sample of it to update it. So let me give an example. Okay, suppose you are on a hill on a hill, you are on a trek. Okay, there are some local tribes on the hills. Some are knowledgeable about the path where you want to go. Maybe you want to go to the top. Some tribes are not very good in explaining the path or communicating with you. They may be knowledgeable, but they may not be able to give you exactly what they mean because you don't understand their language. Now, what do? You don't know. This is a long path. It's a forest, dense forest. You walking around to go to the top, but you don't know that whether these tribes on the way are giving you the right path or not. They may say that you maybe take a left and then take a right and then go, or maybe this path, the other path, maybe there is a valley, so you avoid it. Something they communicate to you. Now, what do? Whether do you take samples so quite often from each of them, or you avoid asking anybody and then take a long route and then decide to ask somebody. Suppose you find so many people around on the way, but you decide not to ask them, or will you ask everyone on every step? That is what is the thing what we are doing here. Whether you want to take this error fully or take a sample of it and then wait for the next sample and then get that error and then take that value. So it is equivalent to you every step, maybe every 10 feet or something, you ask somebody if there are so many people around, so that even if one of the input is wrong, you can still be directed towards the path. So if you are very confident about the inputs what you get, maybe you can have a learning rate which is larger value. But if you are two things, if you are doubtful about the input, or the terrain what you are taking is very dicey, that you don't have the complete information about it. So what do? Whether will you increase this value or decrease this value? Okay, I am not giving you any suggestion. I want you to think about it, because what happens if you increase it, what will happen if you decrease it, you will learn when you try to play around with this on quadratic equation implementation. Okay, so let us wait, let the thinking be around. So right now we have chosen a smaller 0.12 value. It could be much smaller than this or it could be larger than this, but we have decided this. And 200 epoch means we are training the network that many times. That means we are updating the weight and base here that many times. And we run through the complete sample on the model that we have, what we have trained on, and then we compare against the actual and we update it on 200 times. Okay, that means all the inputs are taken, all 120 inputs are taken, we update the weights under 200 times, so that we finally reach which is closer to the actual. Okay, that's what we are doing in the code, and this is what we got. That means this value what we got after this many epochs, we got 1.95 instead of 2 and 0.99 instead of 0.9. Okay, something it will not be same for always whenever you run it, because there is a noise, background Gaussian noise added to the input. Based on that, the learning is also different, so you will get something different around this point. Okay, fine. I think this is what we did. I did explain it on the class yesterday. So let us run through the code now, unless you have anything before. Okay, now let me take the code. Okay, let us keep it like this. Okay, this, let me run cell by cell, shift enter, so that I just make sure that this particular cell, there is no anything wrong with that, and the interpreter has gone through it fully and there is nothing wrong. I am not printing anything here. Maybe I should enable it just to show you what I want to do. Okay, and then we will disable it. So what happens, this is the function on NumPy giving a start value, okay, and the end value, and how many points you want to generate. So from minus pi to 4, I want 120 points to be generated, and it gives me that in a list. So it is inclusive. You can see that minus pi is there, and then line space is equivalent to EQ spaced. Okay, that means there are how many partitions around. Let me, I'm sure you will understand this. Just to be, this is 0, we have minus 5 to 4, so 4 minus 3 minus 2 minus 1, 1 2 3. So how many are there? 1 2 3 4 5 6 7 8 9. So 9 partitions, okay, in terms of 1. So what you do, there are 9 by 120 points you want to generate, which is 0.075. So it is generating a point from here, including 0.5 minus 5. It increments it by, oh sorry, is it 0.075? Let me see whether 9 by 120 0.075, yeah. So this difference, if you see, maybe let me just say that 5 minus 4.9243 6975. Okay, let me complete fully. So 0.075. Okay, so this is how it is EQ spaced, it is giving you. And then I want to shuffle that X in the next one. Why am I doing it? Because I don't want the, this reasoning is very simple. I mentioned it to you. It's like a random walk. Okay, so if you are calculating the MSE, mean square error, if you keep giving the points, actually the line is getting drawn from one end to the other end. Okay, and you are getting the slope, mostly it will be correct, and then slowly you are adding it. Okay, that error maybe it is calculated according to the individual lines, individual points. Now for a straight line, it may not be making a big difference whether you do a shuffle or not, it might learn properly. But in real life, where you have the error function which is fluctuating around, if you are making incremental changes in some way, from starting from some point and then going over the loss function, you may get caught in the local minima. That is not true in our case, but it could be possible in a different scenario, not in the line scenario, because you are not going to get caught anywhere here. The slope is same. But the practice should be that you should not give the input training data which is sequential in nature. Not try to make a random thing so that the model is getting used to the changes and any local minimas are avoided. So it's better to get used to that. That's why we are doing the shuffle here, to just make sure that it is getting a point which are not very close to each other. It is getting distributed all around. So when it is finding the slope, maybe it will be a rough terrain, and it may make initial mistakes, but it will be good for the model to train on avoiding the local minimas. So that's the intent of this. Hopefully I think point is clear. So let me comment of this and then run it. Okay, fine, this is taken care of. Okay, if you have any doubts, I may not know, I may not be sampling your output sorry, chat window, so please stop me and then you can ask me in case if something is not clear. Fine, now what do you do next is, we are creating a random number and of the shape of X. This star gives you that I want this shape. Okay, I want the noise to be generated of the same shape as X. If X happens to be 120, list of 120 elements, this also creates some random numbers which are 120 in number. So we are only taking the shape of X as an input, and then whatever the random number is given, I am adding a 0.3 value. Okay, so let us see what is the value we get. It is the only shape I am printing. So let me print shape and noise. Maybe I should put garage written here. Okay. Yeah. So it is giving you something between some 0.22 minus, in that range. Okay. The values are around that. That's what we are getting. Okay, let me comment of this. So I am generating a different noise at different points, 120 samples I have, and then I'm adding it to the original equation. So now one more thing that I have changed from what I gave you. It's a good practice to have a configurable thing so that you can modify this, and then rest of the code also does not get changed. So use constants preferably. Okay, it is easier for you to change it. I'm sorry, I am showing you something else. Okay, I don't know whether you realized it. I did not realize it. No problem. So, okay, what I showed you was for a quadratic equation, which we are going to be doing an exercise. So, same thing I am doing here. Okay, let me run it here, and the same shuffle is done.
Hello.
Yeah, go ahead.
Sir, what is star?
Okay.
np.random.
Yeah. I'll tell you. Where is it? Missing the point. Okay. See, star gives you the what dimension of input. Okay. I hope, does it make any difference in star or not? No. Yeah. It makes a difference, of course. Okay. Yeah, go ahead.
Sir, basically star is used for zipping and unzipping things, right? Then you have a dimension, column becomes row becomes column and column becomes row. But I cannot relate what exactly this is trying to do. So
Okay.
basically, it will be 2:1. 2, 1. This should be the output of, if x dot shape is, suppose the shape is 1, 120, then
Okay.
star x dot shape will be 120, 1.
One second. Tell me, if shape is
So if the dimension of any particular matrix, say M, is x into y,
okay.
then zipping that matrix,
Yeah, makes it.
sorry, star uh, that matrix, star matrix, and then zipping it will basically transpose it. So what it is doing is changing rows into column.
Wait a minute. Okay.
So x comma y will be y comma x, the shape, the actual shape, because
Okay.
x dot shape is nothing but the shape of the vector, which in this case is 1, 120. The shape of x is 1, 120, right?
Okay.
So doing star will make it 120, 1.
Okay.
But yeah,
1 second. Let me get it. In fact, I didn't spend time on it. Okay. Now 120 and noise is okay. Let me print the shape of noise. It is same, right? The shape remains the same for noise also.
so what does
Hey, see, my understanding was okay. Let us just
one thing, it will be fair if you can take an example, say y equal to say the 20 common, a 2D any, what can I say, Any shape.
Okay.
Uh, um, so basically take y is equal to 1 comma
Okay.
2.
Okay. Is Sandeep right? Who is that?
Yes, Sandeep.
Okay. What do you do?
I'll try.
Yeah, you try and then tell me
Okay.
what you output. Okay. Now
Yes,
after
this
that.
will be
Okay.
yes. Yes.
Yeah. Yeah. Okay. So let us go forward. I did not spend actually time on this, so we will do it later on. Okay. So what do? We get the noise distributed around 120. Sorry, 120 samples. The same shape as the X shape. That's what I am seeing. That okay. Maybe we will see what it does actually. And then what do? We add some value, constant value, so that we get a reasonable amount to be added to the Y value. That's all. Okay, we are doing that. Let me leave out everything except the shape, otherwise it will be unnecessarily polluting us. Fine. Now what do? We add the value to Y, and this is the coefficient which we have defined, 2 and zero point 0.9, and you can see that we get points, and then we will plot it now. So we get 120 points varying from 0 to 30, but distributed around that point value. So we get this input ready, which is of 120 samples. Now this I think you will be able to understand. The scatter plot actually means that we want this dots to be there, or yeah, it is scatter plot is something like this, a plot, and the label is given here, and legend and show is to this, show it on the screen. If you want to save that, we need to give generate the figure and then save figure in the same cell. It saves you whatever is generated in this is saved into a file. So I changed this little bit so that when you are running some other code, you need to make sure that it is not overwriting with what you saved. It will save it on the same directory where this Python file is running from. And tight means it will just wherever the samples are taken, it changes the scale so that you get to see only the points of interest, not from origin or something. It could be anywhere in the XY plane. Okay, so we get an output now. Fine. And then the line model, we are defining it as a class, and this I did not even cover it during our Python course. Call function is one of the magic function similar to new in C++ or creating the object. It actually means that when you pass a value as a if you are calling this model as a function call with some value, it's like similar to calling a constructor. Okay, in C++ word, what happens is your object things are getting initialized, or the object gets created. Okay, and it passes the object reference to the object. So let me explain again. When you want to create a new object of type linear model, okay, with some input, then this is called, you can no this is default, it is called. So one of the examples, I will say, suppose you want to create an object. This is we are not passing any x here. Okay, here we are not creating any passing any x. Now what happens is, if you do this way, it will be doing the init operation. Okay, it will not be creating it with the values of x. It does this. But when you do this linear model of x, when you do, it's like a in C++, I forget, on the go, it creates the object and passes it. Okay, I'm forgetting the exact word for it. If any of you remember that, this is a object which is getting created with the value of x. Okay, with this linear model is already object is there, and you are passing the value and then calling this function. So the original values are here, and then it's like a function call on the object. Okay, similar to function call on the object, but you don't need to specifically call the method. Okay, if suppose you have removed this magic words, you don't need, you need to call it as a method, but here you don't need to call it as a function. As long as the variable is passed, it gets called. Okay, it's similar to a function call. Okay, let me rephrase it. It's not creating the object fresh, it is already, the values are already created and you have an object created here. But using the object, if you pass the value parameter function call, it defaults calls that function, and this x is applied on the object variables, and then you get the return value. Okay, whatever is the calculation, it is not the object, it is getting return. Actually the output of this value is getting returned. Okay, let me get stand corrected. What I meant was, call is for calling a function, and if you mention it as a magic function method, it is default, it calls it. Okay, when you are using the object, a earlier created object, and then you are passing a value, it is equivalent to calling this method with the value. So it applies the whatever parameters are there, the object values, and then returns the computed value. Okay, that's all. We can execute some method using this. Okay, so effectively what we are doing, we are initializing it with some constants, because we don't know what the actual value of this particular model is. So this you can make it any value. Now the question is, if I make it negative, what happens? If I make it a huge number, what happens? That is what you need to play around with and see how your model converges. Okay, how fast it converges. Okay, so I hope this is clear. We have uh, defined a method, class for the line model. Okay, please stop me in case if I confused you anywhere. Now next one is loss function. Now loss function is getting two values. Okay, one is the actual value and the other one is a predicted value of our model, and then we compute. This is also one of the most important thing that we make use of the TensorFlow, mean square error, and we first find the square of the value and we find the mean of it. Now you might think that this is just calling one particular value. Actually you can see that it's a mean, so it's all tensors being passed, and all of them are actually 120 values which are getting passed to it, and then it finds the square of those values, 120 values, and then it finds the mean of them and returns the one single value. Okay, so loss is actually computing, maybe explain it with this picture. What is happening is, once we know the code, we will know this function gets you a array of, okay, or a tensor of 120 values, okay, of x. Okay, maybe I will only take a predicted value, and this is predicted, y and predicted. This is also 120, in our case 120. So they are getting two tensors, and then it finds the square of each values. Okay, it finds the difference and then squares it. Okay, y minus prediction, it finds a square and then returns a different squared values. You'll be getting a different squared value, then it computes the mean of that. Okay, if 120 are there, the squared value is added and 120 is divided, and finally the MSE value is returned. This will be a single float value, but what it is getting is two tensors of 120 each. Okay, now I will explain it when we are really running it. So let us hold on and we will go to forward. Now having written the loss function, we need to train it. Now training, how do you do? Before I come to this code, let me first show you this and then we'll come back. Okay, otherwise logically it may not be correct, clear. Now what I do, I want to create one model, which is done. It has been created. Now what is the values of weight and bias? They are the initial values which I have given, 11 and 12. Okay, done. Then I keep two lists for me to find out how the weights are changing. My weights are initially, I'm calling this as a weight, and so my initial values are 12, 11 and 12. I want to keep observing how this weight value is keep changing as my training goes on. So I want to keep holding those values somewhere. That's why I am declaring two arrays. Epochs, I have decided that I will take it as 120, which I initially, 200. Epochs is 200. So that is the number of epochs. Now, what I do for debugging purpose, I have put this. Okay, maybe I should not. I calling it once to put it. Okay, last function how it behaves. Okay, so maybe it is not needed. Okay, um, let me. What happened? Did I screw up somewhere? Oh, okay. I have to compile everything because partially I did not compile this one. Okay, now okay, so that is the problem. It doesn't, if you miss out some cell, this guy doesn't know that this has been done. So train model is what is happening is when we are just shift right, when you are doing it is executing the cell by cell. So the interpreter is maintaining the state of the program as we keep compiling it, and it doesn't do the rest of the things when you say shift enter. Now since I did not do anything here, and then I came here and then did a shift right, it doesn't know that this function exists, this train function exists. So I gave an error, it gave an error that this doesn't know that train function exists. So I have to go it in the same order. That's the problem we had. Now I just printed this initially to just tell you that x, y and loss values are what dimension they are. So x happens to be 120. Okay, list of that and y is again is a original value which we computed it. Where did we do? We did it here, equation, because x is 120. So what you get here also is 120. So, and what is the output loss value? It is a scalar value. That's why you see an empty set. Okay, so it's a scalar value, just to show that these are the shape which is going in. Now what we do, epoch count is initialized. No, okay, epoch is initialized and 200. This is for loop, and then what we do, we get the weight of from the linear model, whatever is the current weight. Okay, and I am interested in only the value of it, not the tensor or whatever the dimensions are. So I am extracting out the numpy value and appending it to my weight list. Because this is the initial value I am starting with, and this is the initial bias I am starting with in the first iteration, and then I am going to call train. Now train, what do you do? I am passing the object linear model with the original initial values that I assumed that weight and bias are having, and x is the actual noisy input I am giving, and y is the actual output of my function. Okay, y value is actually the original y value of that x. Okay, that I am passing it. Now what happens to the linear model? I made it as a default parameter, learning rate. Maybe you can modify it if you want to. I decided to have it as a 0.12, and then this is the most important part of the code. The gradient tape is a method of TensorFlow which is actually recording the values of different computations that happen in the context. Okay, within this context. So it may not be very logical in our case here, but still this is also valid here. If you do not compute the value within this particular context, what happens is the gradient function cannot operate. Okay, this current loss what I give needs to be computed here. Now why is it so? The reason is the TensorFlow library internally registers the values which are being computed, and while in a normal case in a network where multiple layers are there, you go through that and then you compute the gradient of, you do the backward propagation to compute the actual error, and then the values that you are finding it as a, based on the loss you find whatever is the value, then you update it. Okay, so let me explain what is happening here. This is actually gradient tape is like a, if you have a network of things, you do a gradient computation, and then actually what you do is, when you are updating the value, backward propagation when you do, back propagation when you do, only you are updating the bias and the weight. So it needs to know the sequence of operations that has happened, so that when it is going in a backward direction, it will know the sequence of operations done, so that it can compute the changes to the constants or coefficients or bias that it needs to do by back propagating. It should know what are the operations that has been done, so that it can backtrack it to compute the slope. Okay, but compute the gradient values. Okay, so it uses the if you know chain rule in terms of computing the uh, different in a calculus, you might have learned about chain rule, but it doesn't matter if you don't know also. But this is what is happening during this time. Okay, so you need to compute the current loss, whatever you are feeding it to the gradient inside this. The crux of the matter is you should do this way. Now suppose if I don't do it, if I comment off this and then I do this loss computation outside of this and pass a value to it, okay, then the gradient does not compute the value. Okay, you get the empty values here. Okay, so you need to have this computation internally, so that you remember that. Okay, now what is happening is, we are computing the loss of between y, which is the actual value, and the predicted value of y from the x. Now if we go to linear call, this is what is getting called during this time, and the x is passed. Now x again, remember, is 120. Okay, list of 120 values. So it gives you the new y value, y predicted value of 120 out of it, and it's like a list of array values, and then that is passed to the loss function, which is defined here. Sorry. And now what happens, it is getting both 120 entries of y actual value and the predicted value, and it computes the error between them and square of those values. It's all tensors. Okay, if a tf something is there, you remember it is all operating on the tensors, and it computes the mean value, returns the one float value, which is a output, which is current loss. Now it has gone through individual values and then computed the current loss. So this tape is equivalent to a recording the tape. Okay, so it's supposed to record those sequence of operations done, so that when it is finding the gradient, it will know what values have been computed earlier. Okay, now what you do by calling that gradient, tape.gradient remembers the values or computations that have happened during this time. Okay, by the time you came into the context and before you call the gradient. Now the value what you are getting is current loss. Initially maybe it is huge, and then we are passing, always this gradient function takes two values. I need to check whether it allows more than this, but here we are using only two things at a time. One is weight and bias. Now what are we doing? We are passing the, again in Python is the references. So we are passing the linear models, the internal variables, to this. So the gradient, it updates that. Okay, I'm sorry. Does it update it? No, it is actually taking those values. Let me check it again. It is getting the. Uh, wait a minute. No, it is updating here only. We are assigning the value here only. We are only passing the value, two values. Okay, weight and bias, and then it returns the LR weight and LR bias means you are supposed to compute or the final value. You are supposed to do it with the line rate. Learning rate. You can multiply it with the learning rate. That's why I have put it as a LR weight. Before the learning rate is applied, I have whatever the values it has given, that is the final bias weight update it is giving you. Okay, let me explain maybe with a picture. What is it doing? You are passed, okay, you have passed the current loss that you have computed from the loss value of the mean square error that you have computed to the gradient, and gradient is also uses the computations which have happened here, and then it gives you finally applying a back propagation algorithm inside, tells you finally what is the error or update that you need to do on the weight and bias. Okay, if you assume it to be a one neuron, so many inputs have come, you have a bias, and then you want to some update a weight, then you are this gradient function gives you two values. What is the weight and bias values that you are supposed to update it with? Actually, it is telling you that you take this weight and bias and update your model, okay, directly. But we have some doubts on, not on the gradient, but we have some doubts on the input that we gave it to the model. So we don't want to take it as it is. We want to apply some learning rate on top of it, and then append our weight, assign the, oh yeah, subtraction is there, assign with subtraction. Now I understand. So what we are passing here, it has already been updated, and then we are subtracting this value, I think. Okay, let me, I need to be very sure. I'm sorry, I should have done it. Any one of you have verified it? Otherwise, I need to give this assign.
Hello.
Yeah, good.
Sir, I don't know in TensorFlow, but in PyTorch, what happens is after computing gradient, suppose we are updating x, and after computing gradient, which is basically the slope at that point, what it gives you is delta x,
Okay,
which you should be adding to x. So what we are doing basically here is x plus LR into delta x. So we are not completely taking the delta x. We are multiplying it with LR and then adding it to it.
adding or subtracting? Assign sub.
Sub means substitution maybe.
Okay. Yeah,
I don't know,
subtraction.
but this is how it works in PyTorch.
I
Gradient
think,
gives the delta x, and then you multiply it with the LR, and then you add to it.
now why are we passing these two here?
So
Uh,
this is basically because there are two things that we can update. One is the weight, linear dot weight, which we have assigned in the linear model class, and the bias. These two are variables which can change. And current loss is the value which we are trying to minimize.
correct. So my doubt is whether is it updating it or not. I need to check it. Okay, maybe one of you can do that.
So
Whether
we can print it, no?
I print it, but the problem is it will be too many.
We
uh,
can try to.
yeah.
Yes. No, because the number of epochs are also not much high. We can print it here
Okay.
itself.
Here only you are saying?
Yes, sir. Linear weight dot numpy, because we are adding it, right?
Yeah,
So
yeah.
anyways we will get it because below in the code I saw that we are appending it to the weight array, which
Yeah.
will be. So we will anyhow get the graph later.
I didn't get you. Okay. Maybe you can try it out and let me know. Okay.
So what
Uh,
I'm telling is
uh,
we are anyhow appending the weights below.
correct,
See,
correct.
so we'll anyhow get the graph thing.
Yeah, yeah. Okay, we will
Yeah.
wait for that. Okay, so
Yeah.
what happened? Okay, so thanks, Sandeep. So what happens here is we have the weight which is multiplied with the learning rate, and we append it to the weight. Okay, so now we will go through this multiple times based on the epochs, and then finally we get the values here. Okay, so current class values are printed, and then I printed the weights also later on. So now you can see that the weight, what happens is the current class is initially very high with because our assumptions were wrong totally, and then it was going down. So I actually played around a little bit. Actually, we don't need to do this many things. If you actually look at it, it is not improving further at all from almost here. So 200 is too much actually. We can somewhere stop here. Okay, 104 or 100 is enough. 200 is too much. Okay, because we are wasting time. So we need to look at the loss value, what you get, whether it is coming down or not. Either if your model is not improving further, do not waste your time on keep on training it for it is of no use. So that optimization you need to do. So 200 is too much here. Okay, okay, fine. Now let us go down, and then these are the values which you cannot make sense out of it. So what I thought, I will add a, plot of that. So let me do that here. So weight was originally, it was somewhere here, and then it drastically came down, and then started settling down here. So you can see that around 100 itself, it is almost same. So we can stop the epochs with 100. 200 is waste. Now one more thing, I forgot. Okay, I wanted to say something, I immediately forget. Okay. Mm, yeah, you can, what you do is you can figure it out this picture is not very difficult. Okay, and then weights also you can see output how it is flowing. So what I want you to do is change this initial value to something else, and then see whether it is converging. Yeah, what I wanted to tell you is, even if you do multiple epochs, okay, even more than what you are supposed to, it will not worsen your model. Okay, the reason is it has already reached the global minima, and even if you do multiple time training, it's not going to make it worse. That much you can be assured of, because it is not going to jump off out of anything or going to lose, but you are only wasting your resources in terms of execution time and the processor's time. So you should not keep training it if you don't get any improvement. Okay, fine. Now what else I want? Finally, this is the weight that we have calculated. 2 is our original model, and we have got it as 2.04, and zero point 0.9 was the constant value, which is 0.88 now. Okay, so what else? RMSE value is 0.07. This is the last value, and this is the final output. So that's all. Okay, I hope this is clear now. Any other doubts you have? I need to clarify that. I should have done that. I not made. Okay, unpack the iterable. Okay, all dimensions are being unpacked to give the shape to random n. Okay, okay. So you need to unpack it. Okay, got it. Thanks. Any other questions, guys? Okay, before I give it off to you on your own, this just one summary of this function. Automatic differentiation is useful for implementing the back propagation. So it, as I mentioned, that during the forward pass, it does the differentiation, and then updating the weights and biases, it does it in the backward propagation. So it remembers the all the arithmetic you have done, calculations you have done, and then it, during the back propagation, it uses it. So that's why we put under the gradient tape, you compute the values and then call the gradient function. Okay, so that's what it means, what you use. Actually, you don't need to do all this, because once you start using the keras, you will, all this implementation details would be hidden. But one thing, someone asked yesterday, that when do you use tf or keras? See, what happens is Keras is not included, all the APIs of TF, all the features of TF is not included in the Keras. So there are some occasions where you need to come to the TF world and use something which you want to specifically, take care of using the TF functions. So it's not, Keras is not a complete solution. Okay. You cannot implement everything that you want to do. So sometimes you need to understand the world of TF also. Fine. So this is what I mentioned about the tape, and then the recorded things computations are kept for reverse mode differentiation using the chain rule. Okay. Fine. We'll not go to the details of this. Now what you want you to do, okay, not me to do. I have already done it. I want you to implement similar to line. Please copy the file into another file and then start doing any changes. I want you to implement this function. Now you can understand that there are two weights in this function. You can call it as weight 1 and weight 2, but there is only one bias. Okay. Don't call it as bias 1 and bias 2 because you will be anyway adding it. It doesn't make sense to have two biases. So you can make it as one bias. Now how do you train it? The training has the limit that one weight comma one bias only you can give, right, to the gradient function. So what you need to do is, epochs you can decide, but you need to train the network, one for the weight and of course bias, and then again call the gradient, one for this weight, maybe a trained bias you can give it here. Okay, gradient you call and do it. Okay, so twice you will be doing it. That loop what we saw, you need to change it there. Now you have multiple options here. How do you want to do that? Let me explain what I mean by that. I'll give you the idea and then leave it to you because I don't want to influence you. You may have a better idea than what I have. So epochs are actually going from 101 to maybe 200 here in our case line equation, but here I don't know how much you have to go. You have to find out. But you have two options. Either completely train the weight 1 for all the epochs. No continuous epochs, you do only train weight 1. Okay, and then you do epochs of so much and only train weight 2 and bias. Of course bias is there in both. That is one option. Okay, this is individually doing it, one option, one epochs completely and then doing it. Another one is, while you do the weight 1, okay, inside this, call the gradient here. Again you can loss function you can call and then call the weight 1, weight 2 and bias here. What I mean by that, on every epoch you call weight 1 and bias, and then immediately with that value you call weight 2 and bias, because the bias is the common between these two. Weight and 1 and 2 are two different entities. We are attacking them individually, but the equation is same. Okay, loss function is going to compute the loss of the whole thing, not the individual values. So it has some influence and it behaves differently when you do it in a different order. Okay, I leave it to you. How do you want to do it? Okay, I hope I am not confusing you in this explanation. So what you do is take samples similar to 120. That is again left to you. I chose -5 to 4 based on what I saw output. Okay, and then you add a white noise to y as you did in a line. Okay, now you need to decide about the learning rate, how much you want. In the line equation we saw 0.12 we used. Now this is a quadratic equation with the two weights which are independently being handled with the gradient function. Okay, there is nothing like you are doing it uniform, one after the other you are doing, or within the epoch you will be doing it individually. Gradient function you are calling separately for this weight and this weight. Maybe bias is common for both. So in this scenario, would you use the same value of learning rate, or would you make it lower than this and try it out, or will you increase it and try it out? Which is better? Where will the network converge? Whether will it diverge? That is what I want you to play around with and analyze it and decide on one thing, and then try to have some reasoning about why it is so and so. Okay, that is one thing, one job you need to do. Now one more thing, when you try to learn with one of these values, sometimes you will get a nan as output. Okay, the float values will be showing it as a nan. That means not a number. Okay, when the floating point representation cannot represent a number during the arithmetic, either it goes to the plus infinity or minus infinity, or maybe it reaches the so low that the value is not cannot be represented as a valid number in the float, then nan will be printed. Okay, so nan means the value what you computed, either it has reached some saturation in terms of the lowest value that you can represent using float, or the highest value that you can do, which is equivalent to plus infinity or minus infinity. Any one of them, four values, it could give a nan. Okay, so that means that your model is diverging, and you need to do something else to make it converge to whatever values you have. So this is, I am giving you just a heads up so that you will not be surprised if you get to see a nan value when you are playing around and learning when you are training the network. Now, how many epochs? Will it be 200? Sorry, 800, I think. No, yeah, 200 I gave earlier. So, will it be 200 or more? What do you need for this? I leave it to you. And how many weights and biases are there? You can see, I already told you. So, how will you train your network? How would you call the gradient tape? How many times will you call? What would you do to make the bias also to be closer to the actual? Okay, I want the bias also to be closer to the actual. So, if you can get it similar to this or even better than this, that will be great. Okay, I finally called it many times the train function, and then I managed to get this. I will not tell you how much epoch I gave you, how much line rate I gave for getting this. Okay, that's what I want you to do, because different people working on the same problem will come up with some different ideas. So I want you to beat this, but don't go overboard, because I don't want you to wait for the training to happen after a day or so. It should not take too much time. So don't give 10,000 epochs and something like that. It's not that much needed. So finally you should get an output like this. Okay, this is what is the experiment to be done today. You can use the same code that I shared or better code that you have already written also. That is fine, but do not use any Keras related API. I want you to restrict to only using what is being shown here. Okay, let us not it is only to understand this portion of it.